Hi. Now, there were quite a lot of people who wanted me to take them through my PCB layout of this power supply board, and that's exactly what I'm going to do here. While I was laying out this board, I did actually capture it in real time. So what I plan to do here is actually play that back, the complete recording of laying out the board at times 10 speed, and add in some commentary on top of that of how I was laying it out, what I was thinking, and the processes and things like that. So let's get onto it. Now, before anybody asks, the package I'm using here is Altium Designer, okay? Say no more, that's the package I'm using. Yes, it's very expensive, I'm aware of that, but that's the tool I've used for 20 years. So here we go. Now, the board itself, when I'm actually setting this up, I've already done the outline of the board. That is actually the first step I'm going to do when I start laying out a board, is to do the outline of it. And this is based on the box. I know I haven't done a video outline the system design and the case it's actually going into, but the template of the PCB that you'll see here in black, the black background, that is already defined as the outline of my board with the little cutouts required and things like that. So that's the first step you're going to want to do to a board, as well as setting up your placement grids. Now, I've already done this because this is a through-hole design instead of surface mount. Most of my components are on an imperial 0.1 inch grid. So what I'm going to do is set my grids, both a component grid and a snap grid as well. I'm going to set the snap grid to 50 mil or 50 thou. It's the same thing. Thou means mil. I'll probably use these sort of terms interchangeably throughout the video. I do tend to use both. So mil is not millimeters. Mil is thou, 1/1000th of an inch. So because the components, things like dip packages, are on a 100 thou or 0.1 inch grid, I'm going to set my snap grid to half that value. When I'm routing, maybe drop that snap grid down to 25 thou or something like that. And the reason you want a multiple of this is so that your tracks, when you take them between pins of your IC, go smack bang through the center. And if you try and lay out an imperial board like this, instead of a metric board, which is what new surface mount components use, if you used a metric grid with imperial components, you're going to end up with the tracks not quite going through the center, and it's all going to get a bit messy. But when I'm designing and laying out a board like this, you're forced to use both imperial and metric dimensions, because I will use metric for things like hole sizes. I'll use 0.8 millimeter hole instead of X amount of thou. So I will also use metric for the dimensions of the board, and possibly placing components and the center of components and things like that. So when I'm dragging around my components, I will actually, I might switch to a metric grid instead of my imperial grid, so that a lot of the components themselves, especially on the front panel components, when you're lining them up, they will be on a metric grid. So I've already set these things up in the background, and I've dumped all my components down, because it's a very important step to get your schematic and all your footprints correct in your libraries as a first step, and then dump them all onto your board. So that's what you'll see here. I've started off, I didn't capture this process on video, unfortunately, but what you'll see when I start out here, I've got a blank board that has the outline already done. I've placed some of the components around the edges, because it's very important. The first thing you want to do is place those fixed components that poke out your front panel on the edges of your board, your connectors, your switches, your, all sorts of things like that. You want those to be exactly where you want them on the edge of the board, and then you fix them, you lock them in place, and then your components that's when you start to get to the art of PCB design, is where do you put your components? How do you lay them out? Which area of the board do you put them in? And so on. So I've already done that. I've placed the components around the outside, so let's get into it. All right, here we are. We've got our main schematic, of course, and I've dumped down all the components, as I've said, and you'll see the menus flash up. Sorry, I can't actually slow this thing down as I'm actually recording this audio narration on top of it. But as you can see, what I'm doing around at the top of the screen there is I'm moving the heatsink around now. I'm playing, and at the moment I'm getting that power connector. There's that 2.5 millimeter, 5 millimeter DC power jack, and I'm just mucking around that top area of the board there just to make sure I've got that power connector on the side I want. And I'm also thinking about the system design at this point, because I still don't have a complete idea in my mind about where everything's going to go and how it's all going to work. And this will actually evolve as I lay out the board, because a lot of this might be dependent upon things I see when I'm laying out. So what I'm doing now is I'm placing down the power traces there from the I think close to 100 thou wide, 80 thou, really big beefy power tracks from the DC input jack. And you'll notice all these wires actually connecting all the components that I've dumped down there. The Altium Designer, the program's just done this for me. It's dumped all the components down, and they're actually net wires. They're called from-tos in Altium speak. In other packages, they might be called, rubber nets, rubber banded nets, highlights like that. Now, what I'm doing here, this is a key part of laying out a board. You'll notice that I've started to group together functional components, functional block. And if you've got the schematic and you're playing along at home here, you'll see that I've divided the schematic into these functional blocks, and that's what I've started laying out here. As I've started laying out just that functional block, I've moved in the components. I'm doing this outside of the area of the board. That's another key thing. I'm doing this out in the dead area, and when I've laid out this little subsection of the circuit, I will take that, highlight it all, and then drag it into the board somewhere as a little module. So I'm developing this thing as a module. You'll notice the one I'm laying out now is actually, there's the MOSFET. This is the microcurrent part of the circuit. So that's its own little module, and there's the drive transistor, and there's the base resistor or the pull-up resistor or whatever for that little microcurrent part of the circuit. And if your circuit is modular like this, then that's what you're going to want to do. And here are the current shunt resistors, all 10 of them in parallel there. And once again, you'll notice that the location of those 10 parallel resistors will change later as the board evolves and I move things around. But that's where I put them for starters, because it seemed like a convenient location. It was down near the power switch on the front panel. The front panel is actually the bottom of the board to give you some orientation. The front panel, the bottom section of the board is the front panel. The top half is the heatsink. That's going to be the back of the project. And if you're not that familiar with PCBs, you always do it looking down from the top or through the board. So even when you're laying tracks on the bottom layer, which I'm not, actually the tracks I'm laying down at the moment are all on the top. So red will be the color, red traces means the top layer, and any traces you see in blue will be on the bottom layer. Now my goal is to actually, with a double-sided board like this, there's only 2 layers on this board. What I'm trying to do here, and what you'll see, is all the traces are in red. You won't see me for quite a long time in this video actually put any traces on the bottom layer, because I want to try and add all of these traces onto the top layer of the board. So I'm effectively routing this board as a single-sided layout at the moment, and just keeping that bottom side free for possibly any last-minute tracks, power tracks, and a big ground plane that I can put all over the bottom of the board. And ideally, for a double-sided board like this, you'll notice that I've dragged and dropped the that subsection up in the top left-hand corner of the board there. There we go. I just moved the power. I just moved the current shunt resistors, those 10 current shunt resistors there. There's my current amplifier, U7, which is going to be right next to the current shunt resistors because it's the current sense amplifier. So it has to be right next to the resistors. You can't have those traces going all the way across the board. The bypass caps are going to be near those caps. This one I'm placing at the moment, that's the output of my voltage regulator. I'm trying to get that down to the front panel somehow, so there's less wiring inside the unit. but you'll probably see that trace change further along in the design process. And you'll see quite a few pauses in the video here, and that's just me just sitting in the background thinking, maybe sipping some water, having a scratching my head and just having a general think about the system design, the layout, and remember, I don't have a clear idea of how this layout's going to go. In fact, I have really no idea apart from that the regulators are mounted on the heatsink at the back, and the switches and pots and connectors are mounted on the front, and that's about it. See, because I've got those fixed voltage regulators at the back mounted on the heatsink, it makes sense to put the circuitry around the voltage regulators up near the top of the board there, or the back end of the board, which is the top edge up there near the heatsink, because you don't want to have to run traces all the way across the board. That will kill your layout completely dead. So the goal of any PCB layout is to try and get functional groups of components and keep them together nice and tight. So that's why I lay them out, functional groups, often on the side of the board, outside of the routing area. I sort of route them and then move the entire routed block into the board. You might see a little bit of that here today. You've already seen some of that up there, but there we go. That big circle there with number 3 in it, that's actually one of my mounting holes. That's a PCB mounting hole. Once again, that's a fixed thing. Once you place down those mounting holes and connectors, you want to lock those in place so you don't accidentally move them. That's a very important concept when you're routing out boards. You're doing a lot of stuff, a lot of things happening. You're editing things, moving stuff, and you don't want things to get automatically pushed and shoved or accidentally moved. So that mounting hole there, number 3, will actually be fixed in location. Now, here it is. I'm concentrating on the top, the upper left corner of the board here, and this is where all my analog stuff will go. This is all my low power analog to digital converter, digital to analog converter, and the op amps and things like that. I've shunted all those up in the one corner of the board because I want that to be the quiet section of the board. So I don't want to have them on the opposite side of the board and run traces all the way across, and it can cause all sorts of issues with ground noise and EMC and all sorts of stuff. I don't have the capability to go into all that detail today. I'll have to do separate videos on each element of PCB design. This is just me just giving you a general overview of what I'm thinking about when I'm laying out this board. There's my 3.3 volt voltage regulator, I believe it is there. So I've moved that up in the top corner up there because a lot of that analog circuitry is powered from that 3.3 volt voltage regulator. My voltage reference will be up there as well, the 2.04 volt voltage reference. And oops, what am I? There I'm dragging in my microcurrent. There you go. That microcurrent circuit I routed before, I'm actually dragging that. I've dragged it from the outside into the board there. So it's already partially routed. And there we go. I'm moving my power trace again to fit that down because the trace was in the way. And I'm just you'll notice there will be a lot of shuffling in this. There we go. I've decided to route out that whole area because now I want to drag in, I believe, my microcontroller. Or that's what I thought about there by moving that power trace. I thought my microcontroller would fit in the center of the board there, but now I'm wiring in the USB connector just to get that over and done with because there's 4 resistors that are associated with that. So I put them near the connector down the bottom, and here I am. This is the microcontroller, the AVR, and I'm wiring in the ISP connector. And of course, I'm going to put the in-circuit programming connector right next to the chip because that's where it needs to be. It needs to talk to that chip. I'm not going to put it all the way on the board. Now, here's an interesting thing. I'm actually changing my schematic on the fly here. I can't remember what I've done. I added an extra bypass cap, or I did something there. I've modified my schematic design, and I've pushed that through to the PCB. Any changes I make in the schematic, I pushed them through. That's right, I added a second bypass cap because there's power on both sides of the chip. So I added an extra bypass cap, and there I am attempting to rotate the chip around. You'll find that that's probably not the, definitely not the final orientation. I will end up rotating that chip again. So as you'll see, pin 1 is on the right-hand side at the moment, U6, directly in the center there. And that connector I just placed, that 8-pin connector, that's the serial interface connector. No, sorry, it's the LCD connector. There we go. It's got LCD written on it. And because that talks to the microcontroller, then I want it very close to the microcontroller. I'm not going to shove it on some side of the board somewhere where I've got to route over 8 traces from the microcontroller right over to the other side of the board. So naturally, I'm going to put something like a serial or that LCD connector close to its source, which is the microcontroller. And I know things are happening a bit fast here. I don't have the capability to really slow this thing down. I've just got it in 10 times speed, but as you can see, it is actually taking shape. And once again, I must have been having a breather here, and maybe I've gone for a drink or something like that, or just generally maybe I'm measuring some stuff, because I will have the components and the box and things next to me right here while I'm actually doing this. Here you go, I'm back into it. So I'm making a lot of system changes as well. There you go, I just moved my voltage regulator there too, because I decided that I wanted my serial connector, that's CN3 there, I wanted that over that side of the board, because I thought I would make like a little riser board, little daughter board that rises up out of that at right angles and then goes out the back of my case to avoid the heatsink. So that's why I added the serial connector over in that corner. On the Rev B part of the board, you'll see that I actually changed that, but we're only doing the Rev A board at the moment, which is not the one that I actually built up. If you've watched the previous videos, you'll see that I didn't actually end up, I got this Rev A manufactured, but I never built it up. I went directly to the Rev B, and there you go. I mentioned before how I might rotate the microcontroller again, and I've done just that there. So now I've got the ISP connector on the right-hand side of the microcontroller, and there we go. I'm just shuffling it around like that, highlighting a bunch of components, moving it around, and you can see I can, if you've routed things in blocks like that, then, and you keep them isolated until later in your layout process, then you'll find that it's far easier than to just shuffle around a bunch of components. You can highlight them, including all their traces, and shuffle things around. Now, you'll still notice that all the traces are red. I'm still on the top layer of the board, and that's very important when you're doing a double-sided layout like this, to try and do as much as you can on the top side of the board. And there's lots of stuff going on in my head which I can't really which I don't really have the capability to speak about here. Some of it's even subconscious things like that, but when I'm laying out a board, I do find that it just magically works in the end, where almost the last trace, after laying out hundreds of components, thousands of traces, that last trace just sort of magically fits into place. And that's part of the art of PCB design, and it's actually quite difficult to teach, because a lot of it is a lot of experience, a lot of innate ability to think about the entire system and how things fit together. And this is one thing, if you're laying out a board which you didn't actually design, then it's going to be harder than if you actually design the whole thing. But because I designed this, I have the circuit in my head, or I've got it next to me on paper. I know exactly, everything's modular on the schematic. I know where the modules go, and I sort of have an idea of the system design as far as the case goes and where the connectors go and things like that. So now I'm working on that microcurrent part again. I've got all the resistors associated with that max chip there, the U2 one, along with a couple of transistors there, the MOSFET and the drive transistor and the bypass cap, and I've routed that, and bam, I'm dragging that in. I tried to drag it in, and I found it didn't quite fit. Oh, it's a bit tight there. But I managed to do it. It just fitted in there. It squeezed in below the LCD connector there on the top. part of the screen there and the connectors in the bottom. And because I'm laying out a single-sided board, it's going to be a kit, and it's fairly important to get the silkscreen designators as well visible. So you'll notice like R18, R17, things like that. I've got those outside of the component instead of on the inside, where they're only visible before you place components. So if you've got the room, then you can actually put those silkscreen designators next to the component that you're actually doing. But sometimes if you've got a really tight layout, you can't afford to do that, or you might have to get rid of the silkscreen designators. You might have to ignore them when you place in components like this. If the silkscreen designators are overlapping other components, you'll take care of that later as a final pass. At the moment, I'm not really caring about the silkscreen designators as such. I might shuffle a few around, but generally I will do that as a last pass. So now I'm sort of starting to join all these modules together now, because I'm now starting to think that, this is looking good. It's looking like it's going to fit. I'm always looking at how many components are left over, how much area I've got left. So I've decided at this point that it looks like it's all pretty much going to fit as I expected. So I'm starting to get a bit more confident. I'm joining the modules together, doing a bit more final layout. There I am mucking around with a few traces, trying to keep them nice and tight. So I know there's going to be more traces through that area later. There you go. I've laid a couple more. So I know intrinsically how many more traces that I've got to sort of join those sections together. And you can see by those rubber band nets as well. There you go. I needed to create a bit more space. Ran out a bit of room. I highlighted a bunch of components, shifted them across a bit. I've made a little bit more room there. What am I doing there? I'm changing the USB layouts there. Shuffle. You saw a little slight shuffle there in like 4 traces. I just pushed them all down, and there we go. I managed to fit in another trace, or not quite. I ran out of room there, right in the center. So there you go. I decided to take that around the top instead of it. It's hard to sort of explain where I'm placing traces and why it's so, because I have a lot of the information up in my head about where I think they should go, where, I'm going to know, okay, I need to at least allow another couple of traces through here. So I better not take one trace through there and then have to use a jumper, or, jump to the other side of the board for 2 traces. So it's a trade-off about how, if I know one trace has to go from one side of the board to the other, just because it has to, there's no other way around it, then I'm not going to do that now. I'm going to leave that until last, or I'm going to take it right around the edge so it doesn't interfere with all the other traces which are close together and have to join modules together. So there's a bit of an order about how you do these things. You're going to do your modules first, keep them as tight as possible, route them as fully as possible, and then drag them into the board as a complete routed module where you need it. And then you start, once you're happy with that, you start tentatively joining the modules together, and then you start thinking about power traces. As you'll see, I've done a few key power traces there. And by the way, my power traces are going to be fatter than the signal traces I'm using. I didn't mention it, but I am using 10 thou traces here. So all of my traces, all my signal traces are 10 thou, with my power traces, and they might be 50 or 30 or something like that. They're fatter, lower impedance, and just to designate that they're actually power traces. That's just a good thing to do. Now, it looks like I've used my first via there. There we go. I've run out of room routing into this microcontroller, and I've determined that I need to now jump to the bottom layer. But with this, the key with making jumps to the bottom layer is to keep them as short as possible. Once again, I'm not going to want to use on the bottom layer to route a trace from one side of the board to the other, because you've just split the board in half and you've completely ruined your routing space for all the other traces on that layer. So you'll notice those blue traces under the microcontroller are as short as I could possibly keep them, so they don't take up too much room on the bottom layer, they don't split. There's another one which was quite short. I'm shuffling a few tracks to actually get it a bit shorter. There we go. You'll notice that I changed a few traces there just so I could save a few millimeters extra on traces on the bottom layer so I don't cut up my ground plane as much. I mean, this is not a high-speed controlled impedance board, so cutting up the ground plane isn't really a big deal here. But if I'm laying out a much more critical board, then those little aspects of just saving a couple of millimeters of trace length just so you can get a slightly bigger ground plane on the bottom, and those sort of things can be very important in high-speed designs where those sort of things matter in terms of maybe EMC compliance as well. The ground plane's a big thing, and you want to chop that up as little as possible. So there you go. I'm laying out the output track there. There's the J2 is my output connector there. That's my output mounting point, and that looks like the constant current source, U4 there. I've sort of tacked it around. It's a low current, so it has a 10 thou trace going to it. And I'm placing a few resistors associated with my output current sense. They're my output current sense resistors, and J4 I believe is the current sense input connector. I've decided to move a few more resistors over to this corner, and I'm slowly dragging components from outside of my board into the board. So you'll find, if you can see, you might see a wide shot soon of how many components I've got left, and there will be very few actually left outside of the board. So I'm slowly bringing them in one by one, and there we go. I shuffled those around, put them vertically, and you'll notice I'm lining up all of the resistors nice and straight as much as I can, because that's a good, it just looks good. If your resistors are just oddballed everywhere at all sorts of weird angles and spacings, and it doesn't look like a professionally laid out board. So you want your components to be nicely grouped, and this is where your snap grids come in. If you're not using a snap grid, well, you're crazy. You should be using a snap grid, but if you're not, or you're using a very small snap grid or component snap grid, then your component's going to be slightly out of alignment with each other and things like that, and your board just ends up looking pretty horrible and amateurish. But if you keep them, a big nice line of resistors will be lovely. Things like that. It just looks aesthetically pleasing, and it just shows that you know what you're doing when you're laying out a professional board like this. Now, this is actually the first through-hole board I've laid out in many years, I think, because I'm so used to doing everything surface mount these days that a through-hole board like this is quite a novel thing for me of late. So it's a different mindset. SMD will be different again, because you can't use resistors to jump things. One of the key with through-hole designs like this, because these resistors are so long, there are 0.4 inches across, you can fit many traces underneath, so you can use resistors to actually jump other traces, 4, 5 or 6 other traces at once, and that's very handy for routing ability and routing density on a double-sided board like this. If you've got 8 layers or something, then things are going to be much easier. Your options are much greater. But but you'll see with this double-sided layout, I could almost have done it on a single-sided board. In fact, if I put a bit more thought and effort into it, it almost comes down to I could have done it with maybe a dozen jumper links or something like that. But these days, there's really, unless you're manufacturing 1 million of these things, then there's not a huge cost advantage to go into a single-sided PCB. So I'm using the double. I plan to have all ground plane on the bottom. As you can see, there's a few little traces on the top there, and now I'm on the bottom again because it's blue, and I'm routing looks like my 5-volt rail. So my 5-volt regulator is at the top of the board or the back of the board. And I need to route that 5 volts through to other parts of my circuit. And as you can see, I'm trying to take it around the outside of the board there on the top of the board. I'm trying to route that 5 volts. So I think I'm going to drop through to another layer here, possibly. I'm thinking about it. maybe I'm having another drink or something like that. There we go. I'm dropping down, and I'm using more than one via there because that 5 volts carries a significant amount of current, or it can do. So you're going to want to use more than one via there. As a rough rule of thumb, roughly 1 via for every half amp, but if you've got some serious current, you're going to want at least a minimum of 2 vias there, and I've used 2 or 3 vias there for routing the 5 volt rail. And you'll notice that this board is really starting to come together now, and I'm probably at this point thinking to myself, I'm pretty darn pleased with this, and I don't think I actually have any or very few components left on the outside of the board to actually drag into here. So now I'm doing a bit more fine detail up there. I'm doing some bypass cap work up the top. What am I doing? I'm down into design rule checking. There you go. I have actually finished the basic layout. So I did a basic design rule check to find what the errors is. That will find points that aren't connected. Actually, circuit nets which aren't connected, and there might be a dozen or 2 left in there. So I'm now starting to lay out those, and I'm starting to connect the power now. I think the 3.3 volt rail, because once you've finished, what I would typically do when I'm laying out pretty much any board is do all the signals first, and then once you do that, then you start work on the power rails. It depends though. It depends how power centric, how important the power the power distribution is to that design. But in general, I'm going to, on a board like this anyway, I'm going to leave that power supply until later, and hopefully, if I've given it enough thought, and I've considered this when I'm laying out the board, either subconsciously or semi-consciously, I guess you could say, then the power shouldn't be too much of a struggle to actually route around the board. There we go. I've done another design rule check. I'm looking through the errors. There might typically be a whole bunch of errors for silkscreen spacing and things like that, but I'm not too concerned with stuff like that. It looks like that I've just had a couple of breaks in my power rails there, and it's told me that, I might have 5 unrouted power nets or something like that. So I'm just tidying those up, adding in a 3.3 5 volt rail nets, now my goal pretty much at this stage is to reduce my error net count to 0, or 0 for all traces and all signal traces and power traces, and the only errors I have left are ground, because you'll notice I've routed no ground connections at all, maybe the odd one on the top layer or something like that, but because I'm going to put all of my ground on the bottom, I'm going to flood fill my ground in there, and this is what I'm doing now. Here we go. It was coincidental. I'm now placing the outline of my polygon around the outside of the board. This will be my ground polygon. So I'm placing that on the bottom layer, and you'll see it. So I'm defining the outline, and then the program will automatically fill in the ground layout. Now what I'm doing, going down the center of the board there, is I'm going to split this ground basically into power and signal side. So all of my power, there we go, I just filled in the flood. I got the flood fill there. I can edit that later. I can tweak the finer things later, but there you go. I've basically created a split ground plane there in my board, and the part on the right side of the board, that ground is all power ground. So it goes from my regulators up the top right down to the down to the output connectors at the bottom and things like that. So all of my heavy current is going to flow through the right side of the board, and all the stuff, that ground plane, the blue ground plane there on the left-hand side, that's all signal ground. So there's no real current flowing through that. So there's going to be no voltage drop through that, and therefore all of my sensitive signal stuff, my ADCs in the DACs, will be at the same potential because they're at the same ground potential, because there's no current flowing through that left-hand blue part of the ground trace. And here we go. I'm doing some 3D model time. Sorry, my video capture program didn't capture that. It looks a bit dodgy, but what I'm doing now is looking at 3D mode, and well, no, I'm going the silkscreen layer now, and I'm shuffling my silkscreen. So I'm going through, doing my final pass, my design rule check. I'm happy with it. It passes. There's no nets left over. My board is effectively routed and finished. And now I'm going through and just shuffling all of the component designators. There you go. I'm moving them around, rotating them, and putting them next to the particular component, making sure they don't overlap any of the pads, because you don't want the silkscreen overlapping any of your pads. That can affect you. Generally doesn't affect your soldering, but it's just not good. And you want your silkscreen designators all the right orientation, all the right size, so it all looks neat and professional. I'm going to add some labeling. There we go, AVR ISP. I added a label right next to the connector, and I did it as an inverse. I'm mucking more around with the ground plane here. I've probably decided that I found a bypass cap not going to the right plane or something like that. So having a little muck around, and I'm, as you can see, I'm continually checking the top layer. That purple one there, that purple trace was a keep out. Now, because I didn't want ground to touch those two pads there, because I was doing a star ground system back to, you'll have to look at the microcurrent circuit to figure out what I'm doing there, but I didn't want the ground, even though those traces were ground, I've created a keep out there which stops the flood, the polygon fill, actually joining. Now what I did just there is I joined, that's the star ground point, I joined my two ground planes in that bottom left-hand corner down there. That's the point at which was my star point around the microcurrent circuit. So that's where I split and I joined the ground planes via the top layer there. And I've added some, there we go, added some nice labeling, EEVblog.com, micro supply. I've added a serial top left there, another label, serial. I'm labeling things out. I'm mucking around, and now, what I'm doing now is doing a pass for hole sizes. So, there we go. I'm going in, checking a footprint to make sure I've got a footprint right. Maybe there was some doubt in my mind that I might have goofed that up. So there you go. I jumped over to the net, opened the data sheet, did a double check. I'm now modifying hole sizes here just to consolidate them. So this will be a last pass. I'm doing a 3D view here. Not very few of my components actually have real 3D models in them, but if you did go to that trouble, then you can get a very accurate representation of what your board is looking like. I'm checking my solder mask expansion there. That's the pink solder mask expansion to make sure that there's that they're not going to break. There's enough clearance between each of those pads. In this case, for the transistor, there you go. I just narrowed my pad on the transistor. I wasn't happy with that footprint. Wasn't happy with the solder mask expansion on that. It would have broken through. Solder would short out between the pins during hand soldering or wave soldering manufacture. So I'm just making sure a good thickness, 4 or 5 thou gap between the solder mask between pads. That would be good enough. Anything less, you get down to a couple of thou, then they're not going to be able to manufacture that. Just like they can't manufacture a 2 thou trace reliably, or if you want them to, it'll cost a fortune. So really, this board is very coarse. It's in terms of, it's like 10-10 design rules. I forgot to mention that before. When I'm design rule checking, I set 10 thou traces minimum, 10 thou clearance. So all of my rules and all those polygon pores, they will have a 10 thou spacing to them. So this is a very coarse board. I could make this at home easily. So any PCB manufacturer in the world could make this. Any backyard manufacturer can easily meet 10-10 rules. And I'm checking my bottom solder mask there, checking the top layer. I've added the open source hardware symbol, and bingo, there we have it. That's our final board. And pretty darn happy with that. I'm not sure what I'm doing now. I'm just mucking around more with 3D view. You'll notice the top part of the board that sticks up, that's had the solder mask removed from it. The reason I did that is just because I like it. It's just a different look. It allows you to mark the bottom of the board, something like that. I'm checking the copper layer, silkscreen layer, individual layers in 3D view. And here's the real power of 3D view. It shows you exactly what the board is going to look like when you get it manufactured. Exactly how the silkscreen's looking. You can see if you can get very high contrast in this mode to see that the silkscreen doesn't overlay any pads or something like that. And bingo, there you have it. There's my final laid out board. I'm feeling pretty chuffed about myself. So I added a little platypus there on the right hand side. Why? Well, why not? And I was quite happy with this layout. I was pretty pleased. There's quite a bit of, especially on the right-hand side of the board, you'll see there's quite a bit of area left. And in the next video, I'll actually show me editing this board from Rev A to Rev B to show you how I took a completed board and then changed things around, ripped up the ground plane, modified a few things, squeezed in some more circuitry, and then redid it. So I'll do that as a separate video. I just wanted to mention one of the final passes here I didn't speak enough about was the drill hole size consolidation there. I would have spent maybe 10 or 20 minutes going through the drill size hole table just to consolidate and make sure all my footprints actually have, or how many drill hole sizes I'm actually using in this design, and actually consolidate them, because you might find that some libraries in your component library might use a imperial drill size instead of a metric drill size. So it might be 0.795 millimeters instead of 0.8 millimeters that you'll use on other ones or something like that. So you want to go through as a final step your drill hole size table, just consolidate all those hole sizes into one. Even if they might be near enough, you might go, oh, okay, I'm using 50 1.2 millimeter holes, for example, and I've got two that are 1.25. Well, can I just make those two holes 1.2 millimeters? And that will, in theory, make your PCB a bit cheaper because there's less tool changes required. It's just a nice professional final step to actually do that and check those sort of things. And once again, I'll do a more detailed design rule check. If I do care about silkscreen over pads, I'll be checking for things like that. Electrical clearances, of course, is a big thing. Maybe component spacing clearances, but because generally I know the size of components, or the silkscreen outline defines the size of the component. I'm not too concerned about components touching each other because I know exactly what I'm doing here. You'll notice that the heatsink up on top of the board, or the back area of the board there, has the silkscreen extending right out outside the board. And is that a problem? No, not really. The PCB manufacturer just chops that off. It's just chopped off in the process of manufacturing the board. But maybe as a final step, I might go in and trim that silkscreen just so it doesn't go off the board. But I keep it there because that is the actual size of the heatsink that I'm using, the outside dimensions. So that helps me when I'm doing a bit of system engineering. So I'm going to leave that silkscreen outline there. I could have done it on one of the mechanical layers or something like that, and that would be a more professional step. If I was doing a really professional level board, I would have other mechanical layers that I'm specifying dimensions and engineering notes for manufacturing the board, that it's 1.6 millimeters and it's it might be gold flash finish and where the routing areas and the routing paths and things like that are. But because this is not a really complex professional level board, there's a few extra steps I wouldn't do there. But in general, I'm quite pleased with that layout. How long did it take me? Well, how long did this video go for? Multiply that by 10, and that's roughly how long it took me to lay out this board. And there was a lot of thinking and other stuff in there. And maybe if I had the libraries better sorted out before I started, I could have saved some extra time and things like that. So sometimes a board might take a lot less time because you're using all existing components that you guaranteed all the footprints are right and everything like that. Other times you might be doing a lot of interactive processing. I might be even going through and changing some components in the middle of the design process here. I might find, I might have been mucking around and thinking, I might have found some other device in some other package or something like that and changed on the fly. Or I might find, I can eliminate that bypass cap because they're so close to each other. I don't need that. I can drop one of the bypass caps, or in the case you saw on there, I think I added a bypass cap in there, just the nature of the layout that I didn't think about or I didn't get that right when I was just laying out the schematic. So you might find that when you're doing stuff on the board, you might have to go and back annotate the schematic and make a few changes and things like that. But as you can see, I think it's a neat layout. It's got the cutouts for the case that it's going to fit into neatly, and have to do a whole separate video on that because there's quite a bit of effort which went into actually figuring out where all the components went and what components I used, like the user interface components like the knobs and the switches and the power connector and things like that, and the heatsink went into this system design before I even started laying out the board, and that constrained a lot of things. And if this was just a board that was sitting in the middle of a case and then I had wiring going out to the front panel and the back panel, then it would have just been a simpler design from a system and a PCB point of view, because it would have just been a square board. There would have been no fancy cutouts. The mounting holes wouldn't have to be in specific locations to meet the supports in the case, and a lot of stuff like that would have been a lot easier. But when you're trying to integrate a PCB like this, like I am, that fits a specific case, then there's a bit more engineering. If you've got a custom case, you might have to worry about the 3D aspects, the height of components, will it foul with the case and things like that. In this case, I didn't have to worry about that. I put a bit of thought into it. The case is big enough. It's not a custom molded thing. But if you're doing a professional PCB layout to fit into a custom molded enclosure, really you've got to think about the whole 3D aspect of the mechanical packaging. Thermal performance comes into it, and things like that. You don't want stuff to overheat. If you're doing high-speed signal design, there's lots of stuff in there to do with transmission lines and controlled impedance stuff, EMC requirements, and all sorts of stuff. But this was just a fairly simple board with a simple split ground plane. I probably didn't have to split that ground plane. Actually, if you're asking exactly why, there's probably not a real genuine electrical reason to do that. Just good practice, really, that I just wanted to separate the right-hand side power, which can carry, several amps or something like that, and it may be switching and doing also, the load might be, because this is a power supply supplying an unknown load, so you don't know what it's actually going to be powering, and that could be doing all sorts of, putting all sorts of strain on that ground system. And if you have one big flooded ground plane, then it might in theory cause an issue. So I just decided to split it out, separate it into low current and high current stuff. In fact, not really analog digital in this case, although I guess you could make the same, call that similar to an analog and digital split plane or something like that. But anyway, there you go. That's the complete layout of the board. I hope you found that interesting. I'll do another video showing the changes from Rev A to Rev B. Catch you next time.